question 4.5 and 4.6, I kind of combined them together. It's on isosceles, equilateral, and right triangles. So it says use a piece of pad paper and a ruler to construct an isosceles triangle. So half of the class try obtuse isosceles and the other half try acute isosceles. So I don't think I have patty paper, but go ahead and put it on your paper and try to draw something that looks like it's obtuse, meaning bigger than 90 degrees, and the two sides are the same on your papers. You don't need a ruler, it's fine, just estimate. If you want to use like the side of your notebook or whatever, you can do that. But you want to try to make it so these look about the same length. And then we're going to connect like this. So the nice thing about using patty paper, my fave, is that patty paper is what? What is nice about patty paper? Why do we use patty paper? It's like translucent or transparent, right? So we can kind of see through it a little bit. Okay, so if I'm folding it on top, so if I take this segment and I fold it on top of this segment, what do you guys think will happen? They'll fit directly on top of each other. This will be 90 degrees there. What do you think about those two triangles? Do you guys see that there's two triangles that are formed? Mackie, with me? These two triangles? What do you think is true about them? They're congruent. They're exactly the same triangles, right? So all of their angles and all of their sides match up. In particular, these angles right here. Those are called base angles. I know it bothers you because I didn't draw it on the base. I'm tricky like that. But base angles are across from the congruent sides. All right, so let's say we have one that's acute. So maybe we have something like that. Do you think we could do the same thing where we fold across that middle line? Would they fold directly on top of each other? Yeah, they would, right? Would all of our angles, all of our sides match up? They would. This is kind of a property of isosceles triangles. When you fold them in half, they're exactly the same, right? So then these two angles would be the same. Right? Would other things be the same? Sure, you could say like this angle and this angle are the same. You could do that. But what we're talking about for our theorem is that the base angles are congruent. So that's what this says down here. So it says the base angles of an isosceles triangle are the angles across from the congruent legs or congruent sides. So when I mean across, I mean going across the triangle to the one that's opposite it. You guys know how when we talked about a right angle, we would say, oh, the side across from the right angle is the hypotenuse. That's what we're doing. We're crossing the triangle to the one across from it. Does that make sense? When we talk about triangles later and we give measurements, we would call these like A, B, and C. This would be little a, like side A. This is little b. It's across from angle B. Does this make sense? So we'll be talking about that eventually. So our base angles are going to be these two angles here. And those base angles will be congruent. So if you have two markings that say that the sides are congruent, then those base angles are congruent as well. Yeah, Rhett?
Can you just go down?
Yeah, I don't know why it popped down like that for me. All right, and then the vertex angle is the only remaining angle. It's the one it's between. So it's between the two congruent sides. So the angle between the two congruent sides. Okay, so it's the one that's not the base angles. So right here, this would be the vertex angle. Oops. And then these two would be base angles. Okay, easy enough. Can we handle that? All right, so we're going to be looking very carefully at diagrams because sometimes we have like two segments marked as congruent in a triangle, and then once we have those two segments, we want to mark the angles congruent. Or vice versa. So if you see the angles congruent, then we can mark the segments congruent. So that's what this says. So it says base angles theorem. If two sides of a triangle are congruent, so if we have these markings originally in our problem, we immediately draw in this and this. Does that make sense? And likewise, if we have these two markings in our diagram, then we immediately draw in this and this. that is going to help you a ton with a lot of these geometric diagrams, because sometimes you see it and you're like, I don't even know where to go from here. But if you would just recognize that you have an isosceles triangle, you can get two of the angles are congruent, right? Does that make sense? All right, so we use that a lot. That's called the base angles theorem. So example 1, so it says use the diagram of ABC to prove the base angles theorem. So a lot of times before we use theorems, right, the word theorem, theorems have proofs with them. So we need to be able to prove it. We know how to prove this. So let's go through the proof really quickly, and then you'll never have to do it again. So it says, given that AB is congruent to AC, so we have that marking and that marking, and AD bisects angle BAC, so these two angles are the same. Prove that B and D are congruent. So that first part was our given. Then it says definition of angle bisector. Well, what did I mark? I marked that angle BAD is congruent to angle CAD. I know you guys love when I spell out words bad. I could have done dab too. So then, reflexive property. So reflexive property is same segment. So do you guys see how AD is congruent to itself? Well, once we have that, we can say that this whole triangle right here is congruent to this whole triangle right here. Our two triangles are congruent. So triangle BAD is congruent to triangle CAD. And our reason is side angle side. Do you guys see our side angle side? Because the AD was congruent to itself. So we have side, the angles between it, and then the side. Side, the angles between it, and the side. Do you guys see the difference between that and like side-side angle? Or, yeah, I guess that's the other one. All right, so B and C, why can we say that they're congruent to each other then? CPCTC. Okay, that proves the base angles theorem. So now that you've proven that, whenever you want to jump from these being congruent to these being congruent, we don't have to go through all those steps. We just say, oh, that's true by the base angles theorem. Does that make sense? So that's the nice thing about proofs. Once you prove it once, you don't ever have to prove it again. All right, so using the base angles theorem, we can draw in several congruence marks in the diagram on the right. So if I see that I have an equilateral triangle, three sides are congruent. Okay, what I can do is I can say, well, that means these base angles are congruent. All right, do you guys see these two markings here? Everybody look up here. These two markings here mean these two angles are the same. What if I rotate it around? What if I have these two are the same? Right? So if I know these two are the same, then I can say, oh, these two angles are the same. Does that make sense? This is why an equilateral triangle is also equiangular. So all three sides are congruent, all three angles are the same. Same with this. So if I have these two markings, I can say, oh, these two sides are the same. If I have these two markings, I can say, oh, that means this one and this one are the same. Right? So all three angles congruent means all three sides are congruent. Okay, so sometimes we're going to talk about corollaries. I think I misspelled corollaries. I think it's an IES. These are statements that can easily be proven using a theorem or a definition. So the corollary to a base angles theorem. It says if a triangle is equilateral, then we can say it's equiangular. Okay, this is something that we just proved really quickly, right? We did that up there. And if something's equilateral, then we can say it's equiangular. Okay, easy? So going back and forth. All right, so let's try some of these problems. These are going to be pretty easy for you, I think. Just make sure you draw on your markings if you need them. Colin, put it away. All right, so number 1. So we have this. So we have these two markings and these two markings. Do you see what angles have to be the same then? Yeah, this has to be a 50 right there. Do you guys agree? These two angles are the same then. So if I have 50 and I have 50 and I have x all in one triangle, then I say x plus 50 has to equal 180. Everybody with me? So I get x plus 100 equals 180. So x is equal to 80. Okay, now look at the other side, the right side of this figure. Do we see another triangle? These two angles must be the same. Its diagrams are so tiny. These two angles right here must be the same. Do you guys agree? So then we're going to say 100 plus y has to equal 180. Because these were y's, right? So what's y? 40. Done. Good so far? All right, looking in the picture number 2. So we have to look for those congruence marks. Do we see the congruence marks here and here? So what two angles are the same? Yeah, these two base angles, right? Right there. Does it make sense? So this one's going to be a y. Do you guys know right away what y is? Ian, you got it? Yeah, it's 70, because 110 plus y equals 180. So y has to be 70. So that means in our picture we have 70 here, but we also have 70 here. And then the other one's x. We don't know x. So we say, well, x plus 70 has to equal 180 as well. So x plus 140 equals 180. So what's x? 40, exactly. Do you like this section? It's really not that bad. Just don't forget to look for those congruent angles or congruent sides. Okay, next one. Now I have congruent angles. I have 44 and 44. So I mark it, 44 and 44. They're the same. So do we get one of our variables right away? Yeah, we get that y is 7. Do we see that? Because if those base angles are the same, those two segments are the same. The legs are the same. So y is equal to 7. Oops. Okay, well now we need to find x. So who can set up an equation for x? X plus what? Yeah, Cassie? Yeah, so she said x plus 44 plus 44. So she went ahead and added them and said x plus 88 equals 180. And now I know you guys are pulling out your calculators, but let's think about it. This is like what I give my second grader all the time, Carson. He loves this stuff. Mental math. He's probably better at mental math than I am. Because I was, I grew up like you did with calculators. Can we do this though? 180 minus 88. So let's do 180 minus 80. What do I get when I do 180 minus 80? 100. Then subtract out another 8. Yeah, Kushul's already there way before you guys. He's like, come on, guys. I got it. It's 92. Did you guys all have 92? Exactly. This is not hard. We can do this. I know it's so tempting to pull out the calculator. I was just saying today, like, you guys grew up with phones. So, like, even things like times tables. Like, getting you guys sometimes to say, like, 5 times 8. Like, some people just don't know that because they just always pull out their calculator on their phone. So, we got to work on that. All right, so next up. The perimeter is 54. So what do we notice about this picture? Yes, it looks like it might be equal angular and equilateral. Is it equal angular and equilateral, and why? Yeah, y has to be 60 if those add up to be 180, right? So if all of those are 60, that means all of these sides are the same. So if our perimeter is 54, that means 4x plus 4x plus 4x has to be 54. So 12x equals 54. Now I just got on your case about pulling out calculators. You can pull out a calculator if you want to. Let's write it as a fraction. So if I have 54 over 12, is there a number that goes into both of those? They're both even numbers, so at least 2. So what do I get when I divide 54 by 2? 27. So I have 27 over 6. Is there a number that goes into both of those? No. 3. 9 over 2. Do we know what 9 over 2 is as a decimal?
3.5.
No.
Oh, sorry,
4.5. So you could write 9 over 2, or you could say 4.5. Does that make sense? We can do this without a calculator, I promise. All right, next picture. Try to draw on all your markings, figure everything out. See if you can do it. What's x have to be? 60, because we have 60 and 60, right? Because because the base angles are congruent. So x also has to be 60, because 60 plus 60 is 120. So 120 plus x is 180. All right, so now for the other one. So we have this triangle going on, and we have this marking and we have this marking. I don't know if those are the same, though. I just marked this with one marking. Oh, yeah, I did. These are marked the same, right? So all 3 of those are the same. So if I have y here, I also have y there. Do I know that other angle? Nope. It's not a right angle. Mine looks like a right angle because I drew it like a right angle. Maya, wake up. All right, what else? What is it, Sophia? What is it? It's 120. Tell me why it's 120. Yeah, Kushal? Yeah, it's a linear pair, right? Linear pair is supplementary. Got it? So we have 120 there. Then we have 120 plus y equals 180. So y equals 30. All right, you guys try 6, 7, and 8. So try 6, 7, and 8. You can discuss with the people at your table. Try them. So I appreciate that many of you are trying mental math here. Okay, yeah. So if you have 58, you need to add it to another 58, right? Because these two are congruent. So when you do that, you get 116. So you have 58 plus 58 plus x equals 180. So 116 plus x equals 180. So when you subtract it over, what did you get for x? 64. Yes, so x is equal to 64. So that's in here. And then it gets a little bit tricky because we have that other triangle that's kind of on the left in the middle. And we have, it's what we call an isosceles right triangle. This is a special kind of right triangle because there's only one measurement that we can have for both of these angles. What does that angle have to be? Like these two angles there. They have to be 45. Did you guys all get that? Because you need 45 plus 45 plus 90 to make 180. So if you wanted to call that like a z temporarily or something, you could. So you would just say, oh, z plus 90 equals 180. So z equals 45. So that's good, though, because now we get 45 and 45, and we knew that x was 64. So we have basically 64 degrees, and then we have 45 degrees, and then we have y. So if I want to find y, they all add up to be 180. Does that make sense? So as I add those up to 180, I get y plus 64 plus 45 equals 180. So what do we get? 109 equals, plus y equals 180, so y equals 71. Did you guys all get 71? Yeah, good. Awesome. That's a tricky one. Kind of used an unknown variable in there. We had to put a new variable in to get there. All right, so this next one. So we have 90 degrees here. What did we just learn about a 90-degree, like a right angle that has both of its legs congruent to each other? What did we learn about this angle right here? It's 45. That's a special one. We call it a 45, 45, 90 triangle. Okay, but then we have this bigger triangle around it. And that bigger triangle has 50, and then it has these two angles down here. What do those two angles have to be down there? A little tricky. 130 divided by 2. Are you guys getting it? 65? Yep. So here's the trick. In this diagram, M is that tiny little angle right there. How did you guys find M? Yeah, you do 65 minus 45 to get M. So M should be 20. So N is 45 and M is 20. Does this make sense? They can get pretty complicated. And then of course on your homework, you know, I had to throw one in that involves like factoring. Cam just shakes his head. Some of you just hate it. You're like, why? Why, Mrs. Cox? That's terrible. All right, so this next one. So kind of the same idea. So we have x, we have y, and then we have 30 there. All right, did anybody figure out how to do this one? Yeah, what do you have? Number 8?
Yeah.
What did you do?
So I saw like a big triangle.
Mm-hmm. Ah, yes. He noticed that these two, or these three sides are all the same. Do you guys see that? So it has to be equilateral. So he knew that all these angles made 60. So he already had 30 for one of them. So did that allow you to find x? So if you had 30 here, this one's going to be 30 as well. So then x is 30. You got that?
Yeah.
And then what'd you get for y then?
I got 120.
Yep. I agree. Do you guys agree with that? I had trouble the first time I did this because I wasn't looking at my markings like I tried to tell you, right? Mackie, put it away. I wasn't looking at the markings. I was just, I was like, wait, I thought it was an isosceles triangle. It's an equilateral. So look at all the markings, and sometimes you get more information, right? All right, so far we have learned 4 ways to prove triangles are congruent. So we learned side, side, side. I just talked about this before class, or before we started doing it. Side, 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 angle, side, side, angle, and angle, angle, side. So it says there is one more, hypotenuse leg. Okay, so this is the only version of SSA that works. Okay, so I mentioned what that was, and the reason it works the way it does is because if we have a hypotenuse congruent to another hypotenuse, and then either leg, it doesn't matter. Do you guys see how if I didn't mark those segments congruent? If I instead did the hypotenuse and then I did this leg, it's still side, side, angle going around. Doesn't matter which leg's congruent. But basically I said if I knew this was 8 and I knew this was 10 and I knew this was 10 and I knew this was 8, then I can always find this distance and those are going to be the same, right? So if we know 2 of those sides are the same, then we can get the third one with Pythagorean theorem. Okay, so number 1. So is it possible to say the following triangles are congruent? So if we have 2 markings down here, and we have this marking congruent to these 2 markings, well, then we could say that this missing marking, and we can also say this angle is the same as the other angle. So are those congruent to each other? Yeah. It would be by, what could I use? I don't know. Yeah, angle, angle, side. You guys see it? Angle, angle, side. Okay. All right, how about the next one? Are those 2 congruent? No, they don't even have the same markings. But even if this one had been 3 markings like the other one, right, it's not in the same position. It's not on the other side of that angle. Do you guys understand what I'm saying? So it wouldn't be congruent then. So this is no. Uh-oh, my little pictures got cut off. Does this have 2 markings on the bottom there? All right, so are these 2 congruent? Yes, because the right angle, we could always find that third side. This is by HL. And then this one, we had 2 markings and then 1 down there. Do they have to be congruent? Trick question. They don't, because this angle, these 2 are the same as each other, but I don't have to use 1 marking for them, right? I don't necessarily know if those are the same as the other angles. So a situation like this one would be if I had an isosceles triangle with these 2 angles are congruent, and I knew this base was a certain size, and then I had that base was the same size, but then I knew these 2 sides were the same. That would be a situation like that, where these 2 bases are the same length, right, and these 2 angles here are okay. They're the same. But I know nothing about the angles of the other one, so I could have like a little short one, right? They don't have to be the same triangle. Does that make sense? Always kind of exaggerate your triangles so you can see if they're the same. Okay? All right, so let's stop there.